this scientific and industry webinar. And first of all, I just want to briefly announce our MSc annual meeting will be held 23 November. So still the abstract is open. Please just submit. The registration is free. We just want to get together and then have our scientific discussion. So please join this meeting. Welcome to joining this webinar series co-hosted by the ARC Energy Separation Research Hub, the Monash Center for Membrane Innovations and Membrane Society of Australasia. And please mute your microphone while the webinar is on and post your question at the bottom so you can just ask a question, and then we will pick up some of the question, and then after Mike's presentation, we will communicate and then watch the answer for his opinion. So we will have a discussion. Just let me introduce Mike Dixon. So he is a global expert in desalination and water treatment technology, working with membrane and thermal technology in Australia, North America, the Middle East, the Caribbean, and Asia. Mike has worked across the entire value chain with technology manufacturers, water utilities, oil and gas companies, pharmaceutical companies, and research hubs. He is the CEO and founder of Synauta Inc., a clean tech startup working with desalination innovators, with the goal is to reduce energy and chemical use using data science and machine learning. Prior to Synauta, Mike was a chief technology officer for WaterNext, Western Canada's water technology accelerator, and the application development manager for NanoH2O, a global provider of RO membranes that leverage the UCLA developed nanotechnology to lower the cost of desalination, with over 300 installations in more than 40 countries in the 3 years from market launch. LG Chem acquired NanoH2 in 2014. The Mike is experienced with the development of intellectual property and the commercialized of new technologies. He has more than 60 publications in international journals and is an author of several books and book chapters. Mike is currently a director of the International Desalination Association board. He has been an editor of IDA Journal and the reviewer of the Journal of Membrane Science and Water Research. Mike was the national president of the Young Water Professions for the Austrian Water Association, and in 2012 won the prestigious IDA Fellowship Award. So his talk today is very interesting. The dream of every operator and researchers, optimizing our energy and chemical consumption with machine learning, saving up to 20% OPEX cost. So let's join me welcoming Mike's presentation for today. So Mike, you can upload your file.
Okay, thank you very much, Sean, and thanks for a great introduction. So today I'm here to tell you more about Synauta, where we've come from and how we're saving the desalination industry up to 20% of their OPEX costs by working on the heart of the desalination process, as we all know, reverse osmosis. So I'm going to talk to you about 5 different things today. About desalination and an intro to Synauta, some results of energy saving approaches, machine learning to optimize reverse osmosis, a little bit about the R&D that we've been working on, and then we'll have plenty of time for questions at the end. So first up, I'd like to introduce our team to you. We're currently a team of about 10 or so people when we include part-time people and a couple of contractors as well. But the team consists of myself, the CEO and founder. So previously, as Sean mentioned, I was working at Nano H2O and decided to found Synauta on the back of a lot of things that I learned about the desalination industry and about reverse osmosis from what I learned at Nano H2O. But more about that later. Kent Brockman is our VP of Software Engineering, who comes to us with great startup experience from locally here in Calgary. And then Cole McLean has joined us from IBM. He has a depth of knowledge in artificial intelligence and a master's degree in artificial intelligence from Barcelona University. And he's our director of data science. Karim Tajer is our CFO. Karim was involved in a lot of startups over the years, including in water and in desalination and in software as well. So an excellent addition to our team. We also have Justin Quaintance, a machine learning developer who came to us straight from the University of Calgary as a graduate, and we helped him train by him spending some time doing a Stanford course in machine learning. Nick Herold is our reverse osmosis applications engineer. He joined us from Osmoflow. He's a Canadian guy, but he spent 2 years down in Adelaide working with Osmoflow, so we welcomed him to come back to Canada and work with us. We also have a PhD intern with the University of Alberta. Sam has joined us to do some research, and it comes to us well supported by the University of Alberta's AMI Centre. So AMI is the Alberta Machine Intelligence Institute, who's a partner of ours. And then Christy Dixon is a product manager, comes to us from SA Water as well, being Australian, and also worked on the Adelaide Desal project, such as myself. So here's a little bit more about desalination around the world. So as I looked over the participant list, it looked like there are a lot of people from the research field. So I thought I'd just share a little bit about desalination and a little bit more about industry to give you a little bit more background on the volume of what we're up to. So there's currently in the order of 20,000 desalination plants around the world. They're of all types of different sizes, anything from a few meters cubed per day, all the way up to currently the largest plant is 950,000 meters cubed per day. So back in 2010, when I was working on the Adelaide Desalination project, it was one of the largest in the world, I believe about top 5, and that's a 300,000 meter cube per day plant. So here's an image of the plant just here. You can see the plant was built in 2 portions. One was built first to try and get water as quickly as possible during the millennium drought. And after further funding came in from the federal government, the second portion was started as well. So you might have caught up in the news. A lot of the big 6 desalination plants around Australia aren't currently operational. The Adelaide plant is currently somewhat operational with a couple of trains of membranes working. They did come up to 80% during the dry period in the last couple of years there, but back down again to low levels. So the desal plants around Australia form a fantastic insurance policy for the country. Whenever the country gets dry now, fantastic, there's plenty of water to be produced. So around the world, every day, 99 million cubic meters of water are produced from desalination. If you compare that, just to give an order of size of how much water that is, that's around 40,000 Olympic swimming pools produced every single day. If you think about it in terms of how many people get their water from desalination, that's more than 300 million people. It's our only climate-independent source of water, whereas water reuse is a fantastic strategy for increasing the amount of water kept in a system. Seawater desalination is the only climate-independent source of water, producing new water to a system rather than capturing the water that already fell from the sky in the system or brought up from the ground in the system. There's a couple of different types, you're probably well aware of this, couple of different types of desalination, reverse osmosis and thermal desalination. During starting up Synauta, we looked at both, how we would optimize both kinds of systems. And given that over 90% of the world's desalination is done using reverse osmosis, we decided we'd focus our efforts on reverse osmosis, and later down the track we might come back to thermal plants. So what's reverse osmosis all about? Of course, we all know well, it's a salt removal technique. It's well applicable to seawater and brackish water. Today I'm mostly going to be talking about seawater technology, but down the track we'll probably be able to come back and tell you more about our brackish water applicable technologies. The really key thing for our business is that energy use on a seawater plant can comprise more than 50% of a desalination plant's operating or OPEX costs. We took this figure directly from GHD, the Australian engineers, and actually in some cases it can be as high as 60%. So this is what was our theory when putting the business together, is if we can save energy on the reverse osmosis stage, then we're probably doing a very good job for the entire plant as well. In the past, technologies have come to the fore that have helped improve the energy efficiency of desalination. Even since the very, very early days of reverse osmosis, there's always been more and new technologies aiming to save energy in the field. And a couple that are noteworthy, I think the biggest impact of any technology in seawater desalination was energy recovery devices. And particularly the most successful has been Energy Recovery Inc., the company out of California, where they're based now. They make up more than 80% of the market when it comes to energy recovery devices. So they've really done a fantastic job of taking a new technology from, I believe, in a gentleman's garage where he put all these things together, working it up to a product that would work, trialing it, and building it into a very, very successful company. More recently, solar plants have made inroads into reducing RO energy costs. A lot of desalination plants now are installing solar panels either on the roof of their plant or next door. The Adelaide desalination plant is a great example of this. They're installing solar panels next door. So the thing is, though, that given now we know a little bit more about artificial intelligence, we're able to reduce the energy use even more by using a technology that is not a mechanical technology, not something physical like hardware that we have to install and disrupt the operations of the plant, but something that is software-based that causes very little disruption indeed. Of course, another technology that was great was Nano H2O, the company that I was working for in California. We did a great job there of lowering the energy and desalination as well by as much as 20%. In some cases, that 8 to 10% kind of range was a usual figure for us at Nano H2O. And we really saw some great success around the industry there as well. So again, that's what got me thinking about, well, how can we use machine learning to really improve energy use? So the problem that we're trying to deal with here is that operators of desalination plants have some really important things they have to deal with on a day-to-day basis. The first most important thing is making sure enough volume of water flows from the plant. So they have an order of water coming from the city or the end user of the water, and they have to meet certain targets. In addition to that, they have to meet the water quality targets. So how salty is the water, and is that below a certain range? They might have boron in the water as well. That's a target that they need to make. So operators of the plant are usually thinking about those two things and making sure everything is shipshape at the plant. And on a day-to-day basis, they might not get time to think about optimization. Some do, but a lot run into scenarios where things happen on plant and they have to go fix it. So let's go through a usual day for a typical operator. So they might come in the morning and they make themselves a coffee and they sit down at the controls and they say, oh, there's an alarm going off. So I have to look after the amount of water the plant is producing. So I better go out and fix that thing. And so they fix the thing and they come back and now they sit back down at the controls and, okay, there's another 10 more alarms or even more alarms than that. And so they spend a lot of their time dealing with these alarms and have very little time to sit down and say, okay, I've got to focus now on doing a whole heap of maths and I've got to do some assumptions here to say, all right, I can optimize the plant. So usually it's very rare that they get around to doing a lot of optimizations to the kind of level that we can do with Synauta. Also, it's really hard to match the design constraints of a plant for an operator. So the designers have months to sit down and make loads and loads of calculations. I recently saw a plant in the Middle East was making thousands of calculations to be able to say, this is our sweet spot and this is exactly how we want the plant to be optimized and I'm going to get my design just right for that. So that's all well and good. The plant is then built and commissioned, and when the operators come around to get handed over the plant and operate things, then it becomes very, very difficult for them to precisely match what the designer wanted. It's through no fault of their own, just things happen on site. And so, months and years even can go past at some plants where no optimization is undertaken at all. And this means that there's a great potential for energy being wasted on site. So here at Synauta, we've thought about what are the real easy ways that we can help the operator out and not cost them too much time because they're really busy doing other things. So we've created this set of machine learning algorithms that can really help save energy on site. We're also working on some chemical algorithms, but today I'm mostly going to focus on the energy part. So our software is really, really simple to use. We don't have a front end or anything like that. We spoke to quite a lot of operators and worked out what tools they are really comfortable with. So rather than introducing a new software, we know every operator knows how to use their Scada system and every operator knows how to use email. So simply our software produces a set of set points for the plant and we email that to the operator. So we work in a couple of phases. I'll explain that in a moment. But in that getting ready phase, the operators see that email, check the set points, and then manually enter that into the Scada system. And if after a while they're really happy with that, then we work on upgrading that to be integrated into the Scada system. So that was our focus on making the software really, really easy to use and not having a huge learning curve or any training or too much training involved with putting things together. And of course, it needs to be really secure as well. So we've designed with security in mind and used tools that were as safe as possible. Incidentally as well, plants may choose to adopt two different methods for connecting to our software. Either they can connect via the cloud, or they can install the software inside the firewall of their plant, particularly for large municipal plants, like an Adelaide or a Melbourne or a Sydney. They're usually going to opt for an on-premise deployment so that the plant is not connected to the internet and not open to cyber attack. So here are those phases in a project that I was mentioning before. So first up, we undertake a demonstration. So in this phase 1 demonstration, we perform an audit using historical data to show how much energy could we have saved. So it's a hypothetical answer. We ask the question, if you had used our software, how much energy could you have saved? And if all goes well there and everybody's happy, then we move on to phase 2. So this is the semi-automated set points part of the system. So this is where we're patent pending and at the moment at the PCT level with our patents. So the semi-automated system, the plant will send us data on a daily basis. We'll process that data and we'll make sure it's validated, and we'll send set points back to the plant, and they will manually enter them, and we'll get some feedback back to see how much energy we save on a daily basis. If everybody is happy with that and the system is working really well, then we move into the fully automated mode. So this is when we connect to the Scada system, and it runs then in the background and no one has to think about it too much. The operators might get a button that says, okay, I'd like to use those set points. But otherwise, the operator then has not too much that they have to do other than look over its shoulder and make sure everything is going in the right direction. So given that a lot of us today are researchers or had been researchers in the past, one of the dreams of many researchers is starting a startup and taking the technology that they've spent, blood, sweat and tears putting together to make work and building that into a company. So I've been really fortunate that I was able to learn a lot about startups during my time at NanoH2O in California, and really learn what makes a startup successful. You might have seen in the bio that Sean gave, I've also worked in multiple accelerator companies. So these are companies that help startups get up and going. So when I was working at WaterNext, we helped about 30 different startups in the different phases that they were in to commercialize their technology. So here's a little bit about Synauta's story and how we got started. So when I was working at NanoH2O, I was an applications engineering manager, and it meant I got to look at a lot of data from desalination plants from all around the world. And whenever I looked at the data, I would look it over, and every time I would say, I really think this plant could be optimized just a little bit here and a little bit there. And I bet if they tweak things just that little bit, they could save 5 or 10% of the energy use on site. Or if they use their chemical routine a little bit differently, then they could make their membranes last longer. And so I thought about this for a couple of years. And then when I heard about machine learning, I thought, aha, that really solves that problem, is that operators don't have time to optimize the plant, and plants can be optimized. So why don't we use a software to be able to do that, and an intelligent one, so that we're not always having to tell it, no, change what you're doing, change what you're doing. That would defeat the purpose. So we started the company in January of 2018. And in the very early days, it was just myself. And I worked closely with the Canadian federal government on some grant programs that they had, and with a local company here in Calgary called Cybera that helps startups get off the ground in the machine learning space. So we did some very, very early and basic trials, and that was successful. And so we could go to the government and say, hey, we're onto something really great here. Can you help us out? So they helped us out just a little bit. And we were able to employ a machine learning person. So we employed Justin Quaintance, who I mentioned before. So he joined a couple of months into the company's life. And together we sat down, and I knew about the desalination and he knew about the machine learning. We put our heads together and we started building some things, and we found things were starting to work. And so we went back to the Canadian government and we said, okay, things are really working now. Hey, would you like to support us a little bit more? So over a year or so, probably 18 months actually, we got a little bit more and a little bit more and a little bit more support until we proved, okay, this could be a really viable technology here. And then Sustainable Development Technology Canada came on board and helped us with a much larger grant that allowed us to employ 6 people at the company. So that's roughly where we're at now. But in the very, very early days, it was quite crude, and things were very loosely put together. For example, we worked out of cafes. So there's an image just here of one of the cafes that we used to work in. We would meet 3 or 4 times a week and then work remotely after that. We'd have a coffee and discuss where things were going and keep things on track. For anyone with any software development experience, we worked out of a Jupyter notebook, which is a very, very basic way of doing things. And even in the early stages of production, we were working simply from that. So in the early days, it was a crude collection of scripts. And over time, we made it better and better and better until it was in the state that it's in today. We were also very fortunate to have great relationships with Osmoflow from my time at SA Water. I knew Hip Lee very, very well, who was previously the CTO of Osmoflow. So he was very, very helpful in providing us some data to get going with things. And off we went. So yeah, after 2.5 years now, we have a handful of customers all over the world, including from Australia, the Middle East, Canada, and Europe as well. And things are going quite well. So I mentioned before, we're well supported by people across Canada and across the world as well. We mentioned SDTC came in to support us for $1.3 million. Alberta Innovates is a local innovation acceleration company that is arm's length from the Albertan government. AMI, the Alberta Machine Learning Institute, they have helped us by giving us advice along the way. And a really great partner has been Aqua Advise, some sales consultants in Spain. So let's turn to the more exciting part, talking about the results and how we're making things happen. So here is the most awesome thing about what we do, is at some of the larger plants, there is a huge potential to save money. So at a 300,000 meter cube per day plant, let's take a couple of the Australian plants are about that size. Perth 2 and Adelaide are roughly that size. So if we were to save them 10% energy, and we're seeing in the order of 5 to 10% energy, depending on the design of the plant and how it's operated, then yeah, we could save them over $3 million. Additionally, it's got a huge impact on the environment too. So you can see some figures just here, but GHD did a study for us earlier this year, and they think we can save in the order of 12 million tons of CO2 every single year if we're to deploy reasonably across the world with our technology. So a huge win for the environment and a huge win for the bottom line of desalination plants as well. So this is what we saw on an initial case study that we did with Osmoflow. We looked at some historic data, and here you can see about 6 months worth of data. So we went through a couple of years worth of data and we said, here's a good patch where we know all of the sensors were working on site, and let's look at how much energy we can save them. So this is our phase 1 historic data audit. So the red dots here represent the energy use of the plant like that actually occurred before any interaction with Synauta. And then the green dots represent the optimized energy use. So you can see at times we make a huge saving. This particular saving is about 18% in this region on a day-to-day basis. And then other times we make less of the saving. So essentially, sometimes we save more, sometimes we save less. It depends on the operations of the plant. But on this plant, on average, we could save 9.7% energy savings. So this is quite good. It's a smaller plant. We are working with much, much larger plants, even over 200,000 meters cubed per day around the world. But this first one to get us going was 4,000 meters cubed per day. It's based in Australia and quite remote as well, hence the instrumentation issues that they have. It's very hard to get an instrument out onto site. But yeah, we saw some really, really good results here. Additionally, it was a seawater plant. It operates a handful of pressure vessels across 4 different trains, and it uses energy recovery devices. So the things that we manipulate on site to be able to do this, the high pressure pump, the booster pump for the energy recovery device, and there's a valve downstream of that energy recovery device. So by manipulating those three things and changing the recovery on a daily basis rather than keeping the recovery flat allows us to save the energy where in other places they can't do that. So this is where the rubber hits the road. We then said to Osmoflow, okay, we want to use the system on a daily basis. We're going to send you a set point every day, and it would be great if you enter that into the system manually. So they agreed and all went well. And in early October 2019, we started using our set points. So in red, you can see here, this is the normalized energy use before Synauta came on site. And then in green, this is after the operators started using Synauta's technology. So there's some key things to point out here. Underneath the gray line here, we actually started on this dot just here. On day one, there was an immediate drop in energy use. And across a couple of days, there was an immediate drop in energy use. So because of this, we know, great, we're saving energy. On this plant, we had to do an internal control system. So rather than running two trains of membranes side by side, the flows changed so much on this site that we had to say, okay, we're going to have to look at just one train of membranes and say what happened before to what happened after. So because of varying conditions on site, the best comparison that we can make is what happened the week before and what happened the week after. So that's fantastic. We immediately saw, okay, fantastic drop in energy savings. Over time, we saw the energy use fall. So the machine learning is getting better with time, and we can see through January here, we were making more and more energy savings. So this is great news. We're continuing the trial now. I've not shown that data because there's a whole heap of holes in the data. Like I mentioned before, because the plant is remote, they had some instrumentation errors. And so there were some patches in the data. But what we're seeing more recently is a continued drop in the energy use over time. So that is fantastic news. From time to time, it stabilizes, but some really, really fantastic results. So a little bit more information on this slide. We also used normalized energy use. So you can appreciate that as temperature and salinity of the water changes, then the energy use changes as well. Of course, more salt equals more energy used. And so we created this metric called normalized energy use to remove the effect of that. So that's great. Here in this graph, we're looking at a very, very simple representation of energy use. So we're currently in the process of uploading our software and integrating with the ignition system or Scada system at Osmoflow, and things are going really, really well, and we're just starting that trial now. So I want to tell you a little bit more about our technology and the machine learning part, not too much more, and then I'm going to leave plenty of time for questions. But essentially, there's three parts to our product architecture when it comes to the technology. We have the machine learning part. So that's the part that learns the history and behavior of the RO membranes and what happens over time. And then there's an optimization part that takes that history and creates the set points for us. And we also added standard mathematics to the equation. So over a lot of experimentation, we found in some scenarios, a prediction is better using a standard mathematical approach, exactly what you would read in the reverse osmosis manuals of the manufacturers. And in other cases, the machine learning was better. So it took a little bit of time to figure that out, but we've now got that buttoned down and to have a system that's really a hybrid between using mathematics and using machine learning, and that gets us fantastic results. Another major part of things is how we actually deploy that. So it's all well and good to have this machine learning technology, but you need a delivery system and a data pipeline to be able to accept data in quite a chaotic state from some parts, and process that data, turn it around, put it into the machine learning, train the model, and then produce results out the other end and send it back. So that data pipeline takes quite a lot of effort to develop. And our approach was to use microservices that are all linked together and communicated using a hub to be able to talk between those pieces. So I won't go into too much detail on the deployment now, but let's talk a little bit more about the products. So reverse osmosis systems are quite complex. Here in this diagram, we're showing, okay, there's a lot of sensors on site. So a lot of data coming into our system as inputs. And of course, it took some time to understand what do we have to do here to fully optimize the system? What's important? What's not important? What do we have to add to the system that might be missing? What needs calculating? What can be done by the machine learning? The real complexity that comes is that the internal workings of a reverse osmosis element, the actual membrane itself, is extremely complicated. I'm sure there's a lot of people on the webinar today who are working with fouling mechanisms of reverse osmosis and other membranes. It can be really complicated as to what is going on. So fortunately, this is where the machine learning really helps out. It learns what is going on with a minimum amount of data and puts things together that a human operator or application engineer, or even us as experts in the field, really have trouble working out. So that's fantastic. That removes that thought piece for us and simplifies things in a lot better way. So those membrane dynamics are the key thing that's going on under the hood of the machine learning. Another complexity here, and this is really where human operators would have a huge amount of trouble, is optimizing multiple trains at once. So I thought about how long it might take me to optimize just one train, and it could take, as an engineer on site, maybe a week or so of working through calculations to get things just right and be confident that I'm going to save energy rather than cost the plant energy. And so let's think about a site. Let's use Adelaide again. Over exactly 20 first pass racks on that Adelaide plant. So think about having to do that for all of those 20 racks at one time. So our machine learning is able to take each one of those racks and think about what are the best flows precisely to set on each rack. And so how, by sharing the load around between the racks on site, how can we maximize energy savings yet again on top of the system that we use for just one rack as well. So that is testing very, very well in a location overseas. So doing very well there too. So breaking down what's going on with the machine learning a bit more precisely is the neural network is the system that we use, and we have a whole heap of inputs and a whole heap of outputs. So to break it down, inputs are things like feed water temperature, feed water conductivity. There's a whole heap of others. We just looked at a process flow diagram before of a few things. We also make some calculations, and that's a little bit of where the secret sauce is. And then we have decision variables. So what are our flows out the other end? And typically we want to see what's the permeate flow and feed flow. Here we've got the concentrate flow, those things. There's a mass balance going on there. So we need to know 2 of those 3 flows. And then the neural network is trained by our machine learning experts. We get all those pieces in place just right. And there's a lot of fine tuning that goes on there for particular plants as well. And then we have outcome variables as well. So this, on an energy saving machine learning, is how much energy is used and how do we minimize that. We want to know that we're hitting a maximum permeate conductivity and not going over. And we want to make sure we're making the right flow for the plant as well and not over pressurizing the system either. So that's a little bit more detail, and not too much more under the hood, but a little bit to whet your appetite. The standard math approach, as I mentioned before, is really, really important. Machine learning has this habit of doing whatever it wants to within a certain context. And so by adding more of the standard math, it helped it train and do things within the laws of physics. So, oh yeah, physics are important. So that really, really helped things. If you're not to put in a physics approach, then it doesn't understand things like the limitations of pumps and the limitations on flux in membranes, those kind of things. So that was an important piece too. On a daily basis for the plants that we work with, we create something similar to this, a cost function, looking at where is the lowest cost and thus the lowest energy for a certain feed flow and permeate flow. So just a little bit more to show you what goes on. And here's just a very quick sneak peek on what is coming down the pipeline for us. So we're looking at some new machine learning techniques, just a couple here. Representation and transfer learning, and through this we're really fine-tuning the things that we do and looking at other things to optimize as well. So I've told you today about energy and how we've fine-tuned that and how our future R&D can help do that as well. We've done some work on cleaning algorithms, and then there's a big question mark there as what next? There's a load of different things that we can do in the reverse osmosis space. More on what's coming down the pipeline. Very soon we'll have that Scada implementation underway. And we use an application programming interface or API to be able to connect to a Scada system. We're looking more on the chemical saving side. We released our first case study, and that's really what I told you about today. And that has given us fantastic inroads to the market, and we're seeing really good uptake within customers around the world. So over the next 6 months, we'll continue to work with customers in Europe, the Middle East, Australia and Canada, and really prove out our technology with them. So thank you very much, everyone. That's what I have to talk to you about today, and over to you guys for questions.
Thank you, Michael. This is a very great presentation and a lot of inspiration for you, how you get the idea for the desalination and how to save energy. And you try to collaborate with the machine learning guy, and then how combine together. And then another very important point is you try to create the startup in Canada. And then now it looks like your software machine learning and works very well, and very good presentation. So we got several questions from your presentation. First question is not really technical question, but it's about Jeremy, and he's from Calgary, and he's curious why the Calgary was chosen as the place for Synauta to start up. So are there any challenges being in Alberta given its struggle to transition and its lukewarm reception to the tech sector? So he's wondering why you select the Calgary and the Canadian funding to develop this kind of new idea. So do you have any, because you have experience in Australia, US, and then you have your company in Canada. It's a very interesting story. So can you please share about why it happened and then what's the best way to make a startup if our members try to make a startup like you?
Sure. Thanks, Sean. And good question, Jeremy. Good to hear from a fellow Calgarian over in New South Wales. So when we started things up, we looked at the potential for funding across Australia, the United States, and Canada, given, like Sean mentioned, I had worked in all three countries. So initially, we're thinking about California. California is fantastic at funding startups, and there's a lot of excitement and support for startups there as well. So being able to take technology to Silicon Valley makes it a little bit easier to get venture capital funding. However, it is extremely competitive. It's not just you, it's 1,000 other companies that are trying to get funding and putting their blood, sweat, and tears into things. So it can be quite competitive. In comparison to Australia and Canada, on a yearly basis, the last time I looked at figures, California puts in fact, just Silicon Valley puts in $72 billion into funding startups. Comparing to the figures that I saw, Canada puts in about 10 billion per year, and Australia put in a couple of billion over 5 years. So you can see from those figures, doing a startup in Australia and gaining venture capital funding is extremely challenging. Additionally, in Australia, I looked at funding for startups, and while funding for researching at universities is very well funded across the country with programs like National Centre of Excellence in Desalination Australia, the prospect for startups is a little bit more challenging. So in Australia, you have to bring at least 50% of the funding before you can get any money from the government. And looking at that and my bank balance, personally, I thought it's going to be a long time before we can get to the 50% funding. It's going to be a couple of years there. So that's not really an option. But in Canada, they're very, very good at helping startups get off the ground. They have a lot of accelerator programs, just like in California. But the government is a lot more supportive of startups. So, for example, I mentioned the government gave us a little bit of money to help hire Justin and get things rolling. That's in the order of a few $1,000s. And if you can make good on that couple of $1,000s, then they'll give you a little bit more, and then a little bit more. And it's all about developing trust that you can deliver on what you said you could deliver, and this technology is going to work out, as well as developing the relationships with the government. A big mistake people make in Canada is going to the government and saying, hey, give me money, instead of, hey, I really need your support. So we went to the government and said, this is going to be a long story and we really want your help over a long period of time. Can we get your support in understanding how to commercialize the technology as well? So that's essentially why we settled on Calgary. Could have been anywhere in Canada, could have been Toronto, could have been Vancouver, but I had moved to Calgary and had set up a network in the startup space, participating in an accelerator program called Creative Destruction Labs as an advisor. And that really helped get things off the ground. So I hope that answers your question, Jeremy. Hopefully it wasn't too long-winded either.
I think this question is almost several days discussion together with Jeremy. So you
Absolutely.
can meet together in the Calgary and then discuss together. So next question is about from Greg at the AMS Filtration in Australia, Adelaide. Okay. And do you think that your software could look at the nano and micro cross-flow filtration on their titanium membrane filtration unit? They use a lot of sensors, but probably take the most of them. So do you think the microfiltration looks like they have a titanium membrane as a pretreatment in desalination? So your machine learning also can be combined with the microfiltration as well, not only RO.
So far, we've been focusing on reverse osmosis. So many researchers have heard of Eric Hook from UCLA. In fact, he was the inventor of nano-H2O's nanotechnology. Eric started up a startup called Water Planet in Los Angeles and had a breakout of that called IntelliFlux. They've been doing a really good job of machine learning for ultrafiltration units. So I think they would do a lot better job than us. We're quite focused on the desal part of the technology. I'm not sure whether they have a system set up to be able to do titanium membranes, but if the inputs and outputs are very similar, which I appreciate they would be quite close, both being microfiltration, ultrafiltration techniques, I don't think it would be a huge stretch for them to help. So yes, we could do it, but there's other companies doing a great job.
All right. Next question is from Xiwang Zhang. So does machine learning control the process directly or just give a staff the instruction on how to optimize?
Okay. That's where our phase 1, phase 2 comes in.
Yeah.
So initially we give instructions or insights, recommendations to the operators so that they have a time period to become comfortable with what we're doing. After they're comfortable, then we plug that system into the Scada and it does it itself, and no one has to touch it. So the answer to Ziwang's question is both.
All right. Okay, next question is from Swai Pei Zhao from Deakin University. So during the optimization by machine learning, do we need to modify any parts of whole desalination process, or just control? You mentioned about the boost pump, feed pump, and then energy recovery you can try to manipulate and then save the energy. So you don't need any modification seriously. So that's this question.
Certainly not any hardware modifications. The beauty of our technology is that it's only software. Nothing needs to be installed. On a desal plant, as soon as you start saying, oh, I want to install this instrument or change this pipe around, then it becomes very, very difficult for the operator to say yes. So this is something that can be done relatively quickly and get going on things. So good question there. In the pre-treatment, as we change recovery, the pre-treatment is going to change. Most plants have their pre-treatment flow paced to the RO, so not usually a problem. Certainly we've been operating on a few plants with pre-treatment and not seeing any issues there at all. So yeah, good question.
All right. And no more question from our chatting panel. So just I have one question, Michael. So just wondering, you are targeting on desalination, seawater desalination. It looks like wastewater reuse in Australia was like a large market, a lot of fouling issue more than seawater desalination. So if you want to apply your technology to wastewater reuse RO system, because normally the RO system has no energy recovery device because of low pressure. In this case, your machine learning, because you are manipulating boost pumping, feed pumping, energy recovery device, so how this can fit with water recycling RO system?
Great question. Additionally too, on a water reuse plant, they're not spending anywhere near as much on energy as a seawater plant. And so, yeah, okay, we could probably save them in the order of 5 to 10% energy savings. But at that kind of level, the dollar value is not very high. So instead of working on the energy optimization for a reuse plant, we work on the chemical system. So optimizing, for example, what they dose or their cleaning regime to say, okay, we know at your plant chemical is the bigger thing that you're spending money on compared to energy. And so let's focus on saving you chemicals as much as possible. So we have been doing that at a couple of plants. It's very early days on that one, but maybe if I come back to talk to you again, I can tell you more about that.
That's great. That's great. Also, last question. We have a lot of early career and students in this seminar room. So you're talking about research, R&D. So if we want to collaborate with the Synauta, so do you have any kind of procedure, and then a lot of new idea, machine learning, AI optimization? Looks like young people, they can try to incorporate your technology for the seawater desalination. So what's the your protocol to collaborate with the Australian researchers and students?
Sure, we would love to talk to people, particularly early career researchers. That would be fantastic. Having been an ECR member of the MSA myself a few years ago now, we would love to talk to people. So the process would be really simple. You've got my email on the last slide here. Please give me a buzz and let's have a chat.
That's great. So we are happy to collaborate with your new idea and technology. So please, keep in touch with MSA members, and then we are happy to work together with Synauta. Thank you for your wonderful presentation, Michael, today.
Thanks, Sean. It's been a pleasure to be here.
Thank you. And just to want to have one simple announcement. So as I mentioned, we have MSA annual meeting, so 23rd of November. So still